Hi, this is Sudeep and I welcome you back to this wonderful journey of learning structure analysis with StatPro. From the last session, we started learning about the area moment of inertias. We had seen how we can derive the moment of inertias using the first principles for some very simple cross-sectional shapes. In this session, we will study how we can calculate the moment of inertia of composite sections, and we will learn one very important theorem along with that, which is called the Parallel Axis Theorem. But before we go into that, please take a moment to subscribe to this channel if you are new, and please press the bell icon for more notification from the Structural Insider channel. So what do you mean by a composite section? A composite section is a section which is combined of or composed of several simple shapes. For example, consider an I section. An I section is a section which is composed of three simple rectangular sections. For example, one rectangle is the top flange. The other rectangular section is the web between the two flanges. And the last rectangular section is the bottom flange. So, how do we calculate the moment of inertia for a composite section, like an I section? Well, for that we would need to know the parallel axis theorem. So what is this theorem? Let us find out. Now, this is an area, an arbitrary area, and let this be the centroid of the whole area, and let us consider this to be the axis about which we want to find the moment of inertia. Now, let a small part area be considered within this whole area, which is of the total area, let it be A, and let this be the centroidal axis of this small area. So let this be Y and let this be Z. Now let us consider a small area, small elemental area dA, okay, which is at a distance of y from the y-axis, from the centroidal area of this part area, and let the distance of the centroidal axis of this part area from the centroidal area of this whole area be z. Now, our intention now is to calculate the moment of inertia of this part area about this axis, which is the centroidal axis for the whole area. So how do we do that? Okay, so let us consider this elemental area here. So then the moment of inertia about the z-axis for this part area would be given as dA into this distance, right? So it would be y plus z whole square. Now, this would then be expressed as y square plus 2yz plus z square dA. Now, we can then write this as y square dA plus 2yz dA and z square dA. This then can be expressed as, now this is what? This is the moment of inertia of this part area about the y-axis. So this is Iy. Now this term would vanish. Why? Because this is something that is drawn about the centroidal axis, so this term would vanish. So what would remain is, so this one is constant, right? Because this is a distance between two fixed axes. So then we have z square dA. So that would mean that Iy plus A into z square. So what does it mean? It means that if you are to find the moment of inertia of a small area which is a part of a larger area about the centroidal axis of the larger area, all that you need to do is you need to find out the moment of inertia of the part area about its own centroidal axis, which is Iy, and then add that with the product of the cross-sectional area of the part area multiplied by product of the cross-sectional area of the part area with the square of the distance between the centroidal axis of the part area and the centroidal axis of the whole area, right? So if you know this value Iy, or if you know the value of Iy, you would be easily be able to transfer that moment of inertia value to this particular axis using this expression. This is also called the transfer formula, or it's also known as the parallel axis theorem. Now that we know about the parallel axis theorem, we want to see how we could find, we'd roughly see how we could find the moment of inertia of this I section that you see on the screen with the various dimensions that I have drawn over here. Now, we would actually solve two problems in detail in the next session on the parallel axis theorem, but this is just to give you an idea how we can calculate the moment of inertia of a composite section like this with the parallel axis theorem. Well, the first thing that we would need to identify is the centroidal axis. Now, firstly, we have to understand about which axis we want to calculate the moment of inertia about. Now, so we want to calculate that about the horizontal centroidal axis. So the first thing that you need to do is to identify the centroid of the whole cross section, which would be somewhere around here. So let this be the centroid of the whole cross section, and let this be the horizontal axis about which we are interested to find. Let us call that as the axis as Z, and so this is the axis about which we are interested to find the moment of inertia about. So now that we have located, the first thing, as I've said, is to identify the centroid and the axis about which you want to find the moment of inertia. Now we have to identify centroidal horizontal axis, because we are the axis about which we want to find the moment of inertia about. We want to identify similar axes at the centroids of these individual components. Or rather, let me reframe. We want to identify the horizon or the axis that would be parallel to the axis about which we want to find the moment of inertia about of all the individual components. So, for example, in this, in the top flange with the dimension of B1 for the width and the thickness of the top flange is T1 in this case, we want to identify the centroidal axis of the top flange only. So let this be the centroidal axis of the top flange. Now we want to identify the moment of inertia about an axis that is parallel to the z-axis for the top flange. So what is the moment of inertia of the top flange about its own centroidal axis that I have drawn? Well, it will be, based on what we have learned, it will be bt1 cube by 12. Now the next thing that we would need to identify is the distance of this axis from the centroidal axis of the whole cross section. So this one would be, so this distance would be t1 by 2, and let this distance be, say, x. Okay, so once we identify the distances, the moment of inertia of this component can be transferred to this component by using the parallel axis theorem. That is, the contribution of the top flange to the moment of inertia of the whole cross section about this z-axis will be then given by the moment of inertia about the centroidal axis, which is bt1 cube by 12, plus the area of the top flange, which would be b into t1, and the distance of the moment of inertia of its own centroidal axis, or rather the distance of the centroidal axis of the top flange to the distance of the centroidal axis of the whole cross section, which will be then, let me rewrite this. So the moment of inertia of the, now we are only considering the top flange, okay? So we are only considering the top flange. So the contribution of the moment of inertia as per the parallel axis theorem would be given by I, so this is top flange contribution, the moment of inertia contribution to the moment of inertia of the whole cross section would be given by the moment of inertia of the top flange about its own centroidal axis, which would be bt1 cube by 12, plus the area of the top flange, so that would be b1 into t1, and that should be multiplied with the square of the distance of the centroidal axis of the top flange to the centroidal axis of the whole cross section, which would be x plus t1 by 2. It should be the square of the distance. So this would be the moment of inertia contribution of the top flange when you are trying to find the moment of inertia of the whole cross section about the centroidal axis of the whole cross section. Now the next thing that we want to identify here is about the web, the central web. So if this is the central web, the next thing that we want to do is to identify the centroidal axis of the web. Let us say it's here, and let the distance here between these two, so if this is the centroidal axis for the web, let us say that the distance here is y. So similar to the above, the contribution of this central web to the moment of inertia of the whole cross section would be given by the area of the web, which would be d3 into t3. Sorry, first the moment of inertia about the centroidal axis, so it would be T3, so it would be given as, remember this is nothing but the moment of inertia of a rectangular section. Similarly, we want to find the moment of inertia of this rectangular section about this particular axis. So it will be what? T3 into d3 cube by 12, and then when we are transferring that moment of inertia to the centroidal axis of the whole cross section, we want to multiply this, add this with the product of the area, which would be given by d3 into 2t3 into the square of distance between these two centroidal axes, which would be y square. And finally, the contribution of the bottom flange similarly would be given by so we want to locate the centroidal axis for the bottom flange like this, and let the distance from the centroidal axis of the whole cross section be given by z. So in order to maintain similarity, we can just say that this distance here is x. This distance here is x. So then we can actually change this expression to x square like this, or change it to x square. And similarly for the bottom flange, we have the moment of inertia about this axis would be plus the product of the area, which is b2 into t2 into the distance between the centroidal axis of the whole section and the centroidal axis of the bottom flange. So it would be given as z square of the distance, so z square. So now the contribution from the top flange is this much, the contribution from the central wave is this much, and the contribution of the bottom flange is this much. So the moment of inertia of this whole cross section about this z axis iz would now be given as I top flange plus I of web and the I of bottom flange. So if we add these expressions up, you would get the moment of inertia of the whole cross section about its own centroidal horizontal axis. Now we will actually do a problem of an I section in the next session where things would get more clear. So we now know how to calculate the moment of inertia of a composite section. In the next session, we will see how we can calculate the moment of inertia of any general section. I hope you have liked what we have discussed today, and if you have, please do press the like button and please press the bell icon for more notifications from the Structural Insider channel. See you in the next session. Till then, bye.